This side. I always think it's fun. Whether you guys realize it or not, I always pay attention where people sit, how they adjust themselves. It's actually not nearly perfect, but a close analogy. Has anybody heard of Fermi Electrons? This is worth a shot. All right, you know how electrons fit into atomic orbitals? They're at different levels and different energies. And as you get farther down on the periodic table, you get more and more electrons. Well, you can't keep adding electrons to the same level. At some point it gets full, and then you have to fill up the next level, and then they get full, and so on. And there's roughly this principle that electrons have spin. It's kind of like angular momentum, which we haven't gotten to yet. But like a bicycle will, when it's spinning, it's more stable, or a top. It's got angular momentum, but it can be spinning clockwise or counterclockwise. So with electrons, they call that spin up or spin down. And if one has a spin up, you can't have another one with spin up. It's like spin, and they pair. They always pair up or something. But they'll usually go individually, and then they'll come back and fill in the holes. Watch the bus or tracks. Quite often, you'll see everybody takes their own seat, right? They often don't sit next to each other. And they'll fill them all up before they have to sit next to some stranger, right? It's just like Fermi electrons. They're going to fill them all up first, then they'll go back in and pair up when they have to. I always remember that. It reminded me of that. So, observation in the real world. So you guys ready for review? Excited? Raise your hand if you feel fairly confident with this stuff. That's good. Who's stressing out? Okay, we got one honest soul here. All right, did you come with questions then?
Me?
Yeah.
I just was going to absorb information and see.
Osmosis, hope it works? Great. All right, well today, the way reviews work are, ideally, you guys would have lots of questions. It fills it all up because I'm answering what you're confused with. So I'm hoping you brought several and you guys will talk more this time, at least you do normally. But I realize sometimes it doesn't happen that way. So I've already written the test. I'll be reviewing off it, seeing if I feel like I've covered things. I got the homework. I got some clicker questions for Chapter 5, which we haven't done yet. We got the textbook, so lecture notes. We got plenty, I'm sure, and I won't get to it all. So I got stuff to tell you, even if you don't want to know. I mean, don't ask. So, anytime today, if you're reviewing your homework or something in the text, raise your hand. Okay? I was going to start with this, give you people a chance to get here and think of your questions. Remember we did some relative motion at the end of last lecture? Where and the battery is falling out. And they don't label which side is plus. There we go. So you got some motion in one direction. While I'm at this can represent anything that's a vector. I started last time with velocity. So if you have a velocity this way and a velocity this way, what we're going to repeat here real fast, it also applies to forces. If you had something pushing this way, but something pushing this way, how they can combine, or accelerations. As long as you're not mixing. You don't take a force and a velocity because you're intermixing different things. But if you draw a force body diagram, you can also draw a velocity body diagram. It'll work with anything that's a vector. Because the point of this is components. I'm going to get to. So if you have a vector to your right and a vector to your left, you just add them together like we've been doing. If they're equal, then there'll be no net motion relative to the table. Does that make sense? If they're going the same speed, or in this case the same force acting on them in the directions, then there's no net. And kind of like that. Of course, if they're going the same way, they add, because they're both in the same direction. But what we're adding now is that diagonal. if it's going this way, no, this way while I move this sideways, except for the transition there. So relative to the table, the cart goes in an angle. So let's see, that was like the cart's going this way, but the board was going this way. So most of you, I had you point last time, it should be obvious that the resultant motion will be somewhere over here. How do you know? You can draw a parallelogram. That's where the sides are parallel. And it'll go there. That'll be the resultant motion. So the car relative to the table, let's say had this velocity. Resultant. That's how it's actually moving relative to the table. So these two we call the components. The components. So the way I've drawn it anyway, horizontally, you have this velocity. So like in the x direction. This would be the velocity in the y direction, since I've drawn it vertically here. Does that make sense? If this value were, let's say, 5 meters per second, and this were, let's make it 4, and this one's 3. Can you tell anything about what the resultant magnitude would be? 7, okay. So I'm going to simplify. Bigger than both 3 and 4. Could it be less than 3 or 4? Because we've drawn it. The lengths of vectors represent magnitudes. Could it ever be less than 3 or 4 the way I drew it? It's not a trick question. It doesn't look shorter, does it? Yeah, it's longer. So that's my point on one is we're not doing trigonometry in this class. If some of you have had this, you can do it with sines and cosines and tangents. You can also do it with the Pythagorean Theorem. The sides of a right triangle, this side plus this side equals this side squared. I mean this squared plus this squared equals that squared. So you can figure it out. And I chose these numbers because I know in this specific case this would come out to be 5. But my point is, in this case, it's bigger than 3 and 4. Because in that direction, it has this contributing and this contributing. And so it's a little longer. If you had a square, let's say you had a force this way and a force this way, you know where it's going to end up, right? That way. And you can see it's longer than either side. The ratio there, if you care, is square root of 2, longer than the sides. Again, through trig or Pythagorean theorem. So if you just start out, let's say you got a vector like this. There's a force. You can break that into components. And you can say, so that's like pushing on something diagonally, you know. Instead of trying to push this perfectly horizontally to move it, I could try to pull up on it like this. I'm kind of, some of my force is up, but some of the force is sideways. And so it might look like this. And the way you do this is you just drop perpendicular lines to the axes, the two directions. So this much is in the x direction. Notice it's not as much as the whole thing, because only part of it's moving it sideways. And then a perpendicular here. These are perpendicular. This would be the vertical component. Again, notice it's less than the resultant there. This is going to come into play more when we move on. It first introduces this in the last chapter, so I wanted to share it with you. Let's say you got something going like this and something going like this. You can still play the parallelogram rule. Draw a line parallel to both. You can see the parallelogram. So it's going to end up like that. And the angles and signs get a little funkier because it's not right angles, but you get the idea. We're going to start doing that when we do projectile motion, because there'll be two forms of motion going on, horizontal and vertical. And it's a lot easier to understand this stuff if you break them into the two components. Any questions on that? Okay. That's all actually, that's more than I wanted to say about that anyway. So, this is a kilogram. 1 kilogram. This is a spring scale that measures force in newtons. If you tug on it, it'll register. What do you think it'll read when I lift this up? Say again, this is making too much noise. 22 newtons? 9.8 newtons? And for those that, let's see, Newton's second law, if we have 1 kilogram, that's the mass. Kilogram tells us that. And yeah, you know this is, we'll approximate 10. Then yeah, we should get 10 newtons of force. Let's see. If I can hold still enough. All right. Ta-da! 9.8. Say that again. 1 kilogram is... So something else to emphasize is, what's the force pair? You got Earth pulling down on the mass with 1 or 10 newtons of force. What's the reaction pair to that? This one's a sort of trick question. The Earth is pulling on the mass. So the reaction is the mass pulling back on the Earth with 10 newtons of force. It's trying to attract the Earth up. Notice they're on different bodies. If your first gut was to say, the way the Earth pulls on this down and the spring scale holds it up, realize both of those are acting on the mass, aren't they? That's your tip-off. That can't be a pair. Now this has weight, and it's 10 newtons down, so it's pulling on the scale with 10 newtons down. What's the reaction to that? It pulls on the scale pulls on the mass with 10 newtons up. So it's pulling on the scale pulls on the mass. See, again, they're on different objects. And since it pulls on the scale with 10 newtons, that's why it's reading 10 newtons. That's how weights and scales work. Questions? So there were two force pairs there. All forces come in pairs, but they act on opposite bodies. When you get confused, I don't know if you've noticed, I've been trying to emphasize, think it through. The mass, or the Earth's pulling on the mass. Just flip it, so the mass pulls on the Earth. The mass pulls on the scale, so the scale pulls on the mass. If we double it, what did I just do to its inertia? I doubled it. If it's got twice the mass, it has twice the inertia. We learned that. And I bet you know what it'll read now. About 20, maybe a little less because we're 10s around it. What do we got there? Yeah, it's almost 20. See, 9.8 doubled is 19.6, so there we go. If I can hold it still. So yeah, you got twice the mass. It takes twice the force to keep it in equilibrium. We're not changing its motion, are we? What's the net force on these masses? You guys didn't sound too confident. What's the net force on the masses? All right, we'll pause. Let's draw it. So I always say, when I get confused, draw a picture. Okay, there they are. I'm going to represent them like this. What are the forces acting on those masses, on the masses? It's weight. And we know what that is. Whoops. 20 newtons. All right. Is it moving down? No. So there must be an upward force. And what's doing that? The scale. The scale pulls on the masses. And how much is it? 20 newtons, because we saw that. What's the net force? Let's say up is positive. So we have 20 newtons up plus a negative 20 newtons down, 0. Net force is 0. Or the other way, if some of you have been doing it, is sum all the forces, and it's the same thing. 0. Which immediately tells us that it's not accelerating, which also tells us you've learned it's in equilibrium. We call that state. It's not changing its velocity. It's not changing its velocity. It's not moving either at all. So how this all fits together. It has inertia. In order to overcome that, you'd have to exert a force. We've done that, but we got more than one force, so you have to combine them all to see what the net force is. This is my way of helping you review. Are we good? I'm seeing a lot of blank faces.
It's Friday.
Yeah, that's true. That's just true. It is Friday. Okay. So that's one thing, though. It's kind of like tension. In the back of this is actually a spring, and it stretches the spring. And how much it stretches it determines where this moves to. They've calibrated it to work that way. But it's like pulling on a rope, which can get confusing. Because it's like, wait a minute, if the spring's pulling up with 20 newtons and the masses are pulling down with 20 newtons, why doesn't the rope feel 40 newtons? Well, some people think. Maybe you. And you're not alone. A lot of people think that. You know, if you pull with 20 and I pull with 20, we can put 40 newtons into the rope, but that's not correct. So if you'll humor me, hold that. Thank you. Dope. All right, let go. So, okay, he's going to have a good weekend? All right, that's good enough. That was my stalling. Okay, so let's think of this through. I'm going to pull on the rope with 20 newtons. We can measure it, but, you know, you can visualize. So what's the reaction to that? What's that?
He pulls back.
He pulls on what? He pulls on the rope. I pull on the rope. We don't pull on each other directly. It's through the rope. So the reaction to me pulling on the rope is, that's right, Eddie. The rope pulls on me with 20 newtons. And so there's a force 20 that way, there's a force 20 that way. One's on me, one's on the rope. Same thing over there. Oh. Yeah, I did. So the rope pulls on him with 20 because it's transmitted through the rope. That's why the tension in the rope's still only 20 newtons. It pulls on you, and then you pull with 20. And yeah, it works out being the same because that's what I'm pulling on. But here's a tip. The next time you do tug-of-war, your turn. You don't win a tug-of-war normally by how hard you can pull. You know, at some point I can pull a little more and he gives, but then he pulls. But usually the tension here is always the same. 20, 20, 20, 20. We're all 20. That's great. How do you win a tug-of-war? We're just oh, I can lean. That would just add to how much I pull. I'll give you a clue. That's what most people do. They slip. All right, I can hold the rope here, but what is actually going to move me relative to the room? Me pushing on the floor. For the friction. I'm going to push on the floor. Say I'm trying to go that way. So I push on the floor that way, right? I'm pushing on the floor that way. Does that make sense? So which way does the floor push on me? I'm pushing the floor that way. Back, Newton's third law. Me on the floor back. That's friction. Thanks for holding me up. I'll let you relax. So actually, your tip, if you're ever in a tug-of-war, it's how well you can push against the floor. If I can push against the floor harder than he can, I'll start moving this way. Or vice versa. You look bigger than me, so you can win. So, grip on the floor is a big tactic on Tug-of-War. But another example of force pairs and tension in a rope and things. You guys thought of any questions yet? Things that have been bothering you? Yeah. Oh yeah, which one? Absolutely.
So can you give the definition of an action-reaction pair?
Yes. And without sounding too facetious, I think we've just done like 4 or 5 examples.
Yeah.
So can you repeat one of those?
What was that?
Can you repeat one of those action-reaction pairs?
Yeah, just the Tug-of-War, where every action.
So I pull on the rope, what's the reaction?
Reaction is the same amount of force pulling the opposite.
Right, notice I'm on the rope's on me, different bodies.
So a person just standing on the ground, there's like the reaction, yeah.
Any excuse I got to jump on the table.
The action would be you, the force pushing down, and then the reaction would be the force pushing up your way.
Yeah, there's 2 things going on there, so it depends on the wording. And this one, it confuses folks, which is why I've said the example a few times. We have Earth pulling me down. So the reaction is, I'm pulling on the Earth. The Earth pulls on me, I pull on the Earth. That's an action-reaction pair. Notice one's on me, one's on the Earth. There's another pair going on. Okay, the Earth's pulling on me, that's right. Well, I run into the table. So I'm exerting a force on the table also, correct? What's the reaction to that? Table's pushing up on me. That's the normal support force. That one's on me, but I'm also pushing on the table. Again, 2 different objects. So that one has 2 action-reaction pairs going on. So if we say, yeah, involve the Earth, we want that one.
So I got that one wrong. I said yes.
Yeah, the same happened to me.
Which number? Is this in 4 or 3? This is in 4. What number?
Number 10.
I want to see how it's worded. Consider the 2 forces acting on the person who stands still, namely the downward pull of gravity and the upward support of the floor. Okay, so we just did 2 pairs, total of 4 forces, but only 2 of them were on me. Earth pulling me down and the table holding me up. So it's like this. My weight down and the support force of the table. Are these forces equal and opposite? Yes, because I'm in equilibrium. There's no net force. They equal to 0. I'm not accelerating. I'm not moving. I'm not changing my velocity. So yes, they're equal and opposite, absolutely. Do they form an action-reaction pair? No, because they're both on me. They can't. That's your first tip-off. An action-reaction pair can't both be applied to the same object. These are both applied to me. So again, the reaction to the Earth pulling me down is me pulling on the Earth. The reaction to the table pushing on me is me pushing on the table. They're all 20 newtons, but they're on different bodies. So yes, both forces on me are equal and opposite. Does that make sense? But they're both on me, so they can't be an action-reaction pair. Yes? Well, we haven't studied the Newton's gravitational force law, universal gravitational. And basically, there's a gravitational force between any 2 bodies, period. Roughly, if you have mass 1 and mass 2, a distance r away, they mutually attract each other through gravity. It's like the Earth and the Sun, or the Earth and the Moon, you and me and the Earth. There's just a gravitational force between them. This attracts this, and this pulls back, equal and opposite. It's the same force for both of them, no matter what their mass is. Newton's. Can you repeat that? Because I don't understand what you're asking.
Well, let's see. So you're standing on a table, and the table's on the floor. So you're pulling up the floor.
Yeah, technically, I'm attracting the table and the floor and your chair and the earth, yes. Well, I was trying to simplify.
But if you put more and more you on top of the table will go up.
Yeah, if I increase my mass enough, we would see an effect on the earth. So yeah, all right, here's the earth, here's the floor, here's the table, here's me. So why am I falling down? There's mass below me. This mass is pretty darn negligible compared to the mass of the earth, so I'm just calling it the mass of the earth. And then my puny little mass of me. The force is between those two. This is pulling me down. Well, I have mass, I'm pulling it up. Equal and opposite force. That's Newton's third law. It's just 180 pounds on me has a lot bigger effect, so I fall, than 180 pounds on the earth, which is huge. It doesn't really, we don't see an effect. But that's between any two masses. Is this helping? If we went to the moon, the mass of the moon, same thing happens. There's a force here and a force here, but this force pair would be less in magnitude than this one because there's more mass here. Gravity's stronger on the earth than on the moon. So if I ate way too many Carl's Jr.'s hamburgers, I would eventually have a bigger effect on this, but I'd be pushing harder and harder on the support force. And if it can't handle that, it can't push back with that same force, the net force will no longer be zero and I'll crash through it. Very good.
I'm still kind of confused as far as like what forces need to be involved for there to be an action-reaction.
All right. Give me any force. Anything you can think of. Something hitting something, something pushing something. A gun. Oh, good one. Okay. The gun exerts a force on the bullet to shoot it out. That one seems obvious, right? Gun on bullet. So what do you think the reaction is? The bullet pushes on what? Back on the gun. Equal and opposite force. It's the same. Whatever force the bullet feels, the gun also feels. Same force. That's why you usually feel a kickback, a recoil. It does push on the gun. But you don't move as far or as fast as the bullet does, right? Why? The mass, Newton's second law. F equals ma. And that inertia. The gun and you have more inertia. So you resist that motion more than the bullet for that same force. Okay, do another example. Anything pushing on something else?
Can you just do the weight example one more time?
Yep.
That's the one I'm kind of having a hard time.
You bet. This is my teacher moment where this isn't a knock at all. Sometimes it takes multiple times to go over this until it clicks. So just my suggestion. If the only time you think about this stuff is in lecture, it might make sense here, but when you have to apply it again later, or test time, Monday, it might not come. It might take 7 times before, all right. So you have me, you have the demos, you can rewatch the lecture videos, you got the textbook, you got the homework. So I'm hoping if you do all these, you'll get enough. So I'm happy to do it again because I realize you don't get it all at once. All right, let's make this the ground. Let's do a scale. And me. Okay. Forces we know about, we've already set them. That's my weight, right? And you guys know how to solve that? It's my mass being accelerated down by the earth. So if the earth's pulling me down, the reaction is? Right. So there's a force here. Force of me on Earth. I could label this one Earth on me. That might help. So the Earth pulls on me. I pull on the Earth. Equal and opposite reaction pair. Both 180 pounds.
Okay, so that's not an action-reaction pair. Why? 'Cause, like,
Oh, I just said it was. This is an action-reaction pair. That's what throws you off, the scale. Let's continue. Okay. The Earth's pulling me down. Why don't I fall down? Why don't I fall down? Humor me. What's the Earth's trying to pull me down, but I'm not going down. The support force. And I'm touching the scale. So the scale is pushing on me up. Scale on me. Yes? What's the reaction to that? Right. Me on scale. So what throws you off is these are all equal in magnitude. Well, I meant to draw them the same length, but you know what I mean. So this is an action-reaction pair. This is a separate action-reaction pair.
Because you have the scale between
Yeah, the Earth is pulling me down. No, this one. Earth on me. That's this. That's my weight. I don't move down. If you're looking at the motion of you, you only look at the forces on you. So over here, the one on me is my weight, Earth on me. Over here, the one on me is the scale pushing on me upwards. That stops me from moving down towards the Earth. That's the support force from the scale. And those are equal and opposite, but this is not an action-reaction pair. And your biggest tip-off is because they're both acting on me, the same object, and that can't be a pair. Did we do it? Light bulb go off? All right. We're going to, you can use this in physics. So a lot of times people go, well, I don't know what the force is. Well, I bet a lot of times you do. Like this one. The force of me on the Earth. If we were to ask you that at the beginning of this semester, what force do you pull on the Earth with? You think, I do? And if I told you I pulled on it with 180 pounds, you'd laugh me out of the room, right? But how would you ever come up with that number? Yeah, you stand on a scale. The scale tells you how much it's pushing on you. That's what it takes to support you. Since you're not moving, that means that's how much you weigh, because that's how much you're pushing down on it. Why are you pushing down on it? Because the Earth's pulling on you with that force. So Newton's third law says, well, you pull back on the Earth with the exact same force. So yeah, I pull on the Earth with 180 pounds. So whatever your weight is, and next time you're feeling a little low or your self-esteem's hurt, remember that. It's a significant force. It just has a wussy effect because the mass is so large. Yeah.
Would you call it then the opposite forces are acting on one object, so it's not an action-reaction?
That would be correct.
No, what do you call it if it's not the action-reaction? Is there a name?
Like this. This is not an action-reaction pair, so does it have a nifty name? No, not really. We just say the force is acting on the same body. This is our force-body diagram to help us determine the motion of this object. The other two forces don't affect my motion because they're not acting on me. But they don't have a nifty name. Yeah?
If it's happening on the same object, isn't that an equilibrium?
If they're balanced. If they're acting on the same object and they're the same magnitude in opposite directions, then we'd be in equilibrium. No net force, no acceleration, no change in velocity. Excellent. But what happens if I don't want to use that one. What happens if you pull on something with a certain force and it's dragging along with a certain amount of friction? This is 10 newtons, this is 10 newtons in the other direction. We're in equilibrium. What if you pull up faster? It's now 20 newtons. But there's still only 10 newtons of friction. What will happen? Yeah, the net force is plus 20 plus the minus 10 backwards. So there's a net force of 10 newtons that way. I think you could see that. This is bigger than that, so it's going to move that way. Now it's not in equilibrium. These aren't equal and opposite, so they don't always have to be like that. Only in that case because we weren't moving. Can you be moving and still in equilibrium? Can you give me an example? There you go. Your car on cruise control. Very good. There's still a force propelling you forward, but there's air drag and resistance backwards. And if they're equal and opposite, you're in equilibrium. The net force is 0, which means there's no net acceleration, which means there's no change in velocity. Let me emphasize that again. There's no change in velocity. Doesn't mean you have to not be moving. It just means your velocity is not changing. Good example. So when you throw something up, Eddie, you didn't remind me, I just remembered. You throw something up, whoosh, whoosh. Let's draw some motion on that. You throw a ball up, certain velocity. It goes up, 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 down, down, not to scale. All right. If that's the velocity up, what else can you tell me about the velocity anywhere else?
The velocity down is shorter at that point.
The velocity down?
Acceleration down.
There's acceleration down here? We'll do that one too.
Not acceleration, sorry, the force.
That's all right. I'll do A. I like A. We'll call it G, right? Is that okay? What else do we know? I know you know something else. Anything? What?
Or are we assuming it's just going straight up straight down?
Yeah, I just spread it out for convenience here. Let's just look at the verticals, the vertical motion. We'll get to that, but I won't torture you yet. Oh, you know something. We've discussed. Well, okay, I'll prompt you. What's the velocity here? See? You knew that. Velocity 0 there, okay. What's the velocity here, right before it hits? You're right. It's that negative v. Remember, if something takes, when did I do that? Oh, I counted, like 1001, 1002, 1001, 1002, close enough. If something falls for a second, how fast is it going at the bottom? If it starts at 0 velocity and it drops for a second, what's its velocity after that second? 10, because that's the acceleration. It's changed 10 meters per second every second. So if I throw it up with 10 meters a second, what's it end up at after a second? 0. Yeah, we can say this is 10 meters per second. We'll call that up. So that means this one is negative 10 meters per second. The change in velocity here in a second is 10. What's the acceleration here? 0, because it's not moving?
It's still being accelerated down, even though it's not moving.
That's my point. It's still being accelerated down. It's still g. What is it here? G, 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 G. Try to be consistent here. So do you see, I'm trying to emphasize the acceleration doesn't change. It's gravity. On its way up at the top and on its way down, the force is always down. It's always being accelerated down at the same rate. But its velocity changes. It starts out fast, that's why it goes up. Slows down a little bit here, a little less v, and then it stops, and then it comes back a little faster, and back to where it started, without air resistance. Does that make sense? Yeah. Don't feel bad.
Okay, the G, when it goes up, it's going up at 10 meters per second squared, or 10 meters per second?
Yeah, maybe I should have chose a different value. 10 meters per second is its initial velocity upward.
What's the 9.8 meters per second squared? That's G.
9.8 meters per second squared is the acceleration due to gravity g, which I usually round as 10. But yes, it's technically 9.8. Yeah. In this case, yes. Yes. But we could throw it up faster, right, at 100. That means when it gets back down, it'll be 100. But acceleration is still 9.8 or 10 meters per second per second.
So it's just the opposite of gravity going up, and gravity going up and gravity going down.
Gravity doesn't go up.
Acceleration of something.
Yeah, you can think of it as it's decelerating here and accelerating here. Or you can think of it as negative acceleration up and positive acceleration. No, yeah, that's not really a good thought. It's always negative because it's always down. It doesn't change direction, the acceleration. It's always trying to pull it that way. It's just that it happened to be moving initially up. So it's just like in your car. You're moving along, right? And you hit the brake. Which way are you accelerating? Point. If you're moving this way and you hit the brake, which way are you accelerating? Point. Yeah, that way. Which way are you moving? You're still moving that way, but it's decreasing until you come to a stop. Well, why don't I throw you a couple other review questions on your clickers and we'll call it good. Oh yeah, lest I forget, friendly reminder, your homework's due tonight, not Sunday night. So you have a chance to look at my explanations and whatnot. Test will be Monday, but your homework's due tonight. All right, there's the session ID, so you go those using ResponseWare can log in. Polling is open. Force interaction requires at least what? Well, let's see how folks are doing. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. 88% two forces. Yay. Yeah. Good. If you didn't,
It keeps kicking me out. It was open, but as soon as I...
are you on Uconnect? Just checking for statistics when I talk to the universities. You're logging in through ResponseWare through the web browser, correct? Polling open. I hope this one will be easier now after our discussion today. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Most of you think D, all of them. That's correct. Newton's third law, action-reaction pair. It's equal and opposite in direction. And they have to occur at the same time. I push on you, it's when you're pushing on me. If I stop pushing on you, you're not pushing on me. Please wait for your presenter to open polling. I don't close. All I'm doing, it's like when you switch between open applications. ResponseWare is always logged in. So you're in right now?
Yeah, but it said it was closed right now.
Well, yeah, it is closed. The polling's closed.
I think that's what she means, like, because it says right now nothing's
When I open a new one, you don't have to re-log in though, do you? Yeah. Well, yeah, I closed the polling, so you're not allowed to vote right now. So it should say not give you access to respond. But you shouldn't have to log in each time. They don't make an app for her version, unfortunately. I complained. Yes, what's your question?
On that question you just asked,
Uh-huh.
would it always be equal? If there's an acceleration, could it be different? That would only be if it's an equilibrium.
Whenever one object exerts a force on a second object, the second object exerts a force on the first. So they're on opposite, different bodies.
Would that would be equal in magnitude?
This is the action-reaction pair. If I push on you, you push back on me. You worry about net force and net in equilibrium when they're on the same object.
Okay.
That'll affect that object's motion, so you have to consider all forces on it. This one, it's one object on a second. The second pushes back on the first. And it's always equal and opposite and at the same time. It gets kind of, doesn't it?
Well, I did go with D, but then I just thought
You're thinking further. Well, good. See, you're thinking. Where are we at? Uh-oh. Okay. Let's see. I think I can get a couple more in for review. Or one. Let's see. Okay. Boulder, it's open, so you should be able to respond. Are you logged in right now? Well, if you're not going to answer me, I can't help. Okay. A boulder falls due to gravity. The reaction to that force on the boulder is. Come on, get this one. Boulder falls due to gravity. What's the reaction to that? Your clue is this is an action-reaction pair it's asking for. It can't be on the same body. So the reaction has to be on a different body. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Most of you think B, the boulder pulling up on the earth. That's correct. Air resistance would also be acting on the boulder, so that can't be it. The boulder is being pulled downward by earth. That's a force on the boulder. That's the force we're initially asked about. All of these, well, that's impossible. So B is the only one that's not on the boulder for one. So the earth pulls on the boulder pulls up on the earth. All right, our time is up, so I encourage you to review the chapter, check your understanding questions, go over your homework, and I'll see you after the weekend.